This video is going to focus on the next wing of our study here in Chapter 8, and that is solution concentration. And so we'll introduce a few units of concentration, and then we'll do some calculations of that concentration here. So when it comes to concentration, usually we can find that concentration units break down into two categories. One that is based in comparing amounts of solute to amounts of solvent. Um, and we see this especially in a unit called molarity, which we will use a lot more when we get to chapter 11. And then there are the more common ones where we take the amount of solute and compare it to the amount of solution. Now, notice that the denominator is really the only thing that changes in either of these categories. But when it comes to the numerator, we also have some variance in terms of, we can talk about amount in terms of masses, but we can also talk about amount in terms of moles. So let's start with probably the one that we're the most familiar with, mass percent. Now, we've used mass percent in a number of different ways when we talked about percent compositions in Chapter 7 or empirical formulas in Chapter 2. This has come up before. Now, mass percent is based upon this idea of mass ratio, where I have the mass of one component of the solution divided by the total mass of the solution. And so we can call this part of it our mass ratio. And the mass ratio here, when we multiply that mass ratio by 100, we get mass percent. Now I want you to pay close attention because I'm going to introduce a couple of more units here, units that you've heard of, units that you've actually used in some of your labs, but maybe didn't have a whole appreciation for their context. And that would be parts per million and parts per billion. Now in parts per million and parts per billion, notice that the mass ratio formula is the same as what it was in the previous slide. This mass ratio is the same for both. What's different is the multiplier. In percent, we multiply by 100. In parts per million, we multiply by 10 to the sixth, otherwise known as 1 million. And in parts per billion, we multiply by 10 to the ninth, which, you guessed it, is 1 billion. So these units here are, pretty much the same. It's the same calculation, just multiplying by different numbers. Now, why would we multiply by different numbers? Well, that comes down to a pretty decent understanding of concentration. Percent, or parts per 100, as it can be also known. Percent is used generally when our concentrations are larger. So I know if I have something that's a 5% solution, I know 5 grams out of every 100 are going to be that substance. But when I get into things that are in smaller quantities, parts per million and parts per billion become a lot more prominent because the difference, that 10,000-fold difference between percent and parts per million is significant. If I want to know the concentration of lead in my drinking water, hopefully that number is pretty close to zero. But if I told you that it was 0.0000001%, yeah, you might be able to look at that and go, okay, that's a small number, but what is its context? However, if I did the same thing and said, okay, well, that's 1 part per million, and the EPA standard is 0.2 parts per million, then you'd be concerned. You go, oh, okay, this is a more serious issue than I thought. So parts per million, parts per billion are used especially when we know that our concentrations are low, and they help to kind of rationalize and bring them up to numbers that we have a little bit more of an easy time understanding. The last concentration unit that we're going to look at here in chapter 8 is molarity. Now, molarity is another very common unit. We have seen molarity a number of different times, especially in our laboratory. Maybe haven't fully always understood what it meant, but it's always been there. Now, molarity is the moles of a substance divided by the liters of solution. And we can use molarity in a number of different ways. In fact, we'll get into this particular use of molarity where we use it as a conversion factor to figure out grams of solvent, or excuse me, solute at a later time. This is actually a really common conversion. This is a way to allow us to do stoichiometry with solutions and not just with solid materials like we did in chapter 7. So let's take a look at some examples here. What is the molarity of an aqueous solution prepared by adding 36.5 grams of barium chloride to enough water to make 750 milliliters of solution? So to answer this question, I have to have a little bit of information. So first of all, I've got to keep in mind my equation. Molarity is equal to moles of barium chloride divided by liters of solution. Okay, so that's where I'm going. Now, I don't have either of those values at this point. I have a mass of barium chloride, and I have a volume in milliliters of solution. Well, one of those is pretty easily fixed. 750.0 milliliters is equal to 0.7500 liters. And that's just a simple metric conversion. If you can't slide that decimal in your head, um, know that there are 1,000 milliliters in a liter. And so if I divide this number by 1,000, that's how I get the 0.75. Now for the conversion of barium chloride, I'm going to need a little bit of help. And that little bit of help is going to come in the form of I need a molar mass. So if I start with my 36.5 grams of barium chloride, I need a molar mass to turn that grams of barium chloride into moles of barium chloride. And so for this, I'm going to need my calculator. All right, there we go. Molar mass of barium is 137.33 plus the molar mass of chlorine is 35.45, and there are two of those. So my total mass, 208.23. And so my calculator out again. 36.5 divided by 208.23, and to three significant figures, I get 0.175 moles. Now to find molarity, I need to do that ratio. So molarity is equal to 0.175 moles of barium chloride divided by 0.7500 liters of solution. And that equals, let's get my calculator out again, 0.175 divided by 0.7500 to 3 significant figures. I get a solution that is 0.233 molar barium chloride. So in simple terms, that's how we can calculate the molarity if we have a mass and a volume of solution. Now, what if we have something else? Let's say that we have a concentration in milligrams per liter. Milligrams per liter is another way of saying parts per million. How can I change that into moles per liter? Well, here's one of those examples. We did combination units in chapter 1, and this is a prime example of just that. Vinyl chloride, the chemical formula for that is C2H3Cl. That'll become important when we have to convert it to moles. So I have 0.002 milligrams of C2H3Cl in 1 liter of solution. And I'm going to get to moles per liter, I already have liters in the denominator. I just need to convert the milligrams to moles. So first step, convert the milligrams to grams. And then the last step, I need a molar mass to convert the mole, the grams of vinyl chloride into moles. So carbon 12.01. There are 2 of them. 1.01 for hydrogen, and there are 3 of them. And then 35.45 for chlorine, there's just 1 of them. 62.50 is my molar mass. Put in my fraction lines here real quick. And get out the calculator again. 0.002 multiplied by 1, multiplied by 1, divided by 1, divided by 1,000, divided by 62.50, and to 1 significant figure, because that's all that we started with, I would have in scientific notation 1, 2, 3, 4, 5, 6, 7, 8, 3 times 10 to the -8th molar vinyl chloride, which we could rewrite in terms of calculator notation 3e minus 8 molar vinyl chloride. Now, you'll see a problem very similar to this on your quiz, where you'll be asked to convert between molarity and percent by mass. And so I will feature a problem like that in a future video, but that's all for this particular video. If you have any questions, contact me. Otherwise, have a good afternoon.